We have started to deal with the problem of Focault's pendulum in the previous lecture, and this is actually the second part of the lecture which we will see today. In the first part of the lecture you have learned that actually the Focault's pendulum is a device for conveniently detecting even slow rotation of the earth, and it provides a direct experimental evidence that the earth rotates about its axis from west to east once in 24 hours. And so that it was confirmed that the frame attached with the earth is a non-inertial frame. You can see in this figure, already this figure has been explained in the previous lecture, that in Focault's pendulum there is a string of length L, which is in original experiment this was 70 meter, okay, and a heavy bob whose mass was actually 28 kg in original experiment. This is suspended from a rigid support from A, and in equilibrium position it is at a point P, and when it is displaced to a point P dash slightly and released, then actually it makes oscillation in a horizontal plane XY, as you can see in this figure. In fact, these X, Y, Z are the position coordinates of the bob when it is at its displaced position. You have learnt that actually apart from the real forces mg and this tension T, pseudo forces were also acting, and we have considered only the Coriolis force because the centrifugal force was neglected due to the very small value of Earth's angular velocity. And we have obtained actually the equation of motion of this bob. Now today we will see the solution of those two equations of motions. What was the equations of motions which we have obtained in the previous lecture? I have mentioned here. So definitely before watching this second part of video on Focault's pendulum, you must watch the first part, because in continuation then you can understand the whole concept clearly. Actually in first part of the lecture we will actually prove that this bob actually traces out an ellipse and that will be proved at first, and after that we will see that how we can say that our earth is rotating. Okay, so let us see. As today's lecture is in continuation of the first part of the lecture on Focault's pendulum, so I have started my lecture here from the result which we have already obtained in the previous lecture, and I have written those two equations directly here because you have learned about this in the previous lecture. You have seen that the first equation of motion for x direction for the bob of this pendulum was mx double dot equal to minus mg times x over L plus 2 m omega sine lambda y dot, and for y direction the equation of motion was my double dot equal to minus mg times y by L minus 2m omega sine lambda x dot. You know what are the different quantities in these equations. Actually L is the length of the pendulum, and m is mass of the bob, omega is angular velocity of the earth, and lambda is the latitude of the place where this pendulum has been suspended. Now the aim of today's lecture is to solve these two equations and at first to prove that the bob will trace out an ellipse. Okay. Now you know that time period of a pendulum is given by 2 pi times root over L by G. This is a well-known formula for simple pendulum, and that can be applied here too. So from here you can see that this 2 pi by T, this will be a square root of G by L, and we have supposed it this is equal to omega naught. Can you think what is this omega naught? Definitely this is the angular frequency or angular velocity of the bob. This is angular velocity of the bob or pendulum, you can say. Mark it. This is because t is the time period of the pendulum. So this represents the angular velocity or angular frequency of the bob or pendulum. Okay. Now we will utilize this result in equation of motion, which I have written here. At the place of g by L, you can see in both of the equations the factor g by L is present, and you can see a square root of g by L is omega naught, so g by L is omega naught square. So we will simply substitute omega naught square, where omega naught is the angular velocity of pendulum, in those two equations. So you can see, again you can see that m is a common factor in both sides. So m will cancel out, you can easily see. Okay. So I have written here only x double dot, and that will be equal to minus omega naught square x plus 2 omega sine lambda y dot, and second equation will be y double dot minus omega naught square y minus 2 omega sine lambda x dot. Okay. Now actually to solve these two equations, we have to cast these two equations into a standard form. And for casting the equation in a standard form, we have to do some mathematics. So this is not physics but mathematics, and you have to remember these steps by practice. Okay. And for this, let us multiply equation, this equation 1 and 2, sorry, not 1, but multiply this equation 2 by I. And after multiplying this equation 2 by I, where I is iota, which is equal to, a square root of minus 1, then we will add this equation 2 to the equation 1. You can see. Now, x double dot plus iy dot, because second equation will be multiplied by I. Okay. So LHS will be x double dot plus iy double dot. Now in see the first term of both equations. In second term I will be multiplied, and you can take this minus omega naught square as a common factor, and so the remaining factors will be x plus iy. And in the second term again you can see I have multiplied the second equation by I. Okay. And we can, if you take minus 2i omega sine lambda as a common factor, then what will be your result? You can see here in the second term of equation 2, this minus 2i omega sine lambda is present, so here only x dot will remain. Okay. But in first equation second term there is no I. So I have written here I, because I times I will be I square, and that will be minus 1, and this minus will make plus. So you can write this equation, this term as 2i omega sine lambda x plus iy. Okay. Now let us bring all these two terms in the LHS. They will become positive, and your equation will become like this. This will be x double dot plus I y double dot plus 2i omega sine lambda x dot plus iy dot plus omega naught square x plus iy, and that will be equal to 0. Okay. Now let us substitute x plus iy equal to u. We introduce a new variable. Okay. And if x plus iy is u, you can easily see that when you will differentiate both sides of this equation with respect to t, that will be simply d prime x by dt, because differentiation, this x coordinate is with respect to the rotatory frame, so I have written d dashed of d dashed, not d, and that will be I d dashed y by dt. And you know, time derivative is written by the dot symbol, so you can write it as u dot equal to x dot plus iy dot. Again, when you will differentiate it with respect to time t, then you will get the second order derivative, and you can write u double dot equal to x double dot plus iy double dot. Okay. Now we substitute these values. It means at the place of u, at the place of x plus iy, we will write u. At the place of x dot plus iy dot, we will write u dot. And at the place of x double dot plus iy double dot, we will write u double dot. Then this equation, you can see here, will be what? This equation will simply become u double dot plus 2i omega sine lambda u dot plus omega naught square u equal to 0. Okay. And you know that this omega sine lambda, this is actually the z component or vertical component of the angular velocity of the earth. You have learnt in the previous lecture. Okay. And because this omega vector makes angle lambda with y-axis, and so its z component was omega sine lambda, and x-axis on x-axis this omega is perpendicular. You have learned this thing in the previous lecture. So at the place of omega sine lambda, here I have written omega z. Okay. Now this equation 3 can be put in the operator form. Here we use an operator d and d square. You can see at the place of u double dot, I am writing d2u. Okay. And at the place of u dot, I am writing du. Okay. So you can see this equation can be written as d square plus 2i omega z d plus omega naught square u equal to 0. Okay. Actually here d is equal to d dt and d2 is equal to d2 dt square, as you can see it here. Okay. Now you can see that this equation is just a quadratic equation. Okay. Because u is not 0, so we can actually equate the bracketed term equal to 0. Okay. So this is d square plus 2i omega z d plus omega naught square equal to 0. Since it is a quadratic equation in d, so we can find its two roots using the formula for the quadratic equations root. So d will be equal to what? According to the formula, this will be minus 2i omega z plus minus root over b square. And at the place of b, there is 2i omega z. So this will be 4i square omega z square and minus 4ac. So minus 4, a is 1 and c is omega naught square. Instead of this minus 1, you can write I square. So this will be 4i square omega naught square. So I have written here 4i square omega naught square. Now you can see that this 4i square is a common factor inside this square root, and that can be taken as a common factor, and when it will be outside of the square root, this will be simply 2i. So your result is minus 2i omega z plus minus 2i times a square root of omega z square plus omega naught square over 2. Okay. Now you can take this 2 as a common factor, and that will cancel by the denominator in 2, and so our result will be what? our result will be minus I omega z plus minus I omega 1. Actually here I have written omega 1 square equal to omega z square plus omega naught square, you can see. Okay. So taking the plus minus sign separately, you can see there will be two values of d1. And what are those two values? When you will take plus sign, let us say then d is d1, and that is minus I omega z plus I omega 1. Okay. And if you take this minus as a common factor, this will be omega z minus I times omega z minus omega 1. And d2 will be the value of d when we will take this minus sign here. So d2 is minus I omega z minus I omega 1. Again take this minus I as a common factor, then your this will be minus I times omega z plus omega 1. Okay, this is just a simple calculation. Now you can see that the solution of this equation 3, this is just a standard equation, a standard differential equation of second order, and you can write the general solution of this equation in this form. This is u equal to a e to the power minus I omega z minus omega 1 t plus b e to the power minus I omega z plus omega 1 t, because the value of d1 and d2 has been obtained here. Okay. Here actually a and b are the arbitrary constant, because you know, since the equation is of second order differential equation, so there will be two integration constants, and a and b are actually those two integration constants. Okay. So you can write this result like this: u equal to a times e to the power I omega 1 t plus b e to the power minus I omega 1 t times e to the power minus I omega z t. Okay. Now, as you have seen that the angular velocity of the pendulum omega naught, which is 2 pi over t, and that is equal to root over L by g, and omega z, this is omega sine lambda, which is z component of the angular velocity of the earth. Now since earth is rotating very slowly, so you can see here that this omega naught will be much greater than this omega z. So I have written here, you can see omega naught is much greater than omega z. In other words, you can say that omega z is negligibly small in comparison to omega naught. And that's why you have seen that omega 1 square is equal to omega z square plus omega naught square. But since omega naught square is much greater than omega z square, so we can neglect this omega z, and we will write omega 1 square almost equal to omega naught square. In that is, omega 1 is almost equal to omega naught. Now we will substitute omega 1 equal to omega naught in this equation 4. Okay, at the place of this omega 1 we will write this. Okay, and we will neglect this term e to the power minus I omega z t, just treating that omega z is so small that it can be taken almost equal to 0. So e to the power minus I omega z t, this will be almost equal to e to the power 0, which is equal to 1. So under this condition, our equation 4 will become what? This will be simply u equal to a e to the power I omega naught t, because you have seen that omega 1 is equal to omega naught, plus b times e to the power minus I omega naught t. Okay. Actually, these two equations which this equation 5 actually gives the trajectory of the path traced out by the bob. Okay. Now you can see, you know the Euler's formula, that e to the power I theta is equal to cos theta plus I sin theta. You know it. Okay. And e to the power minus I theta, this will be equal to cos minus theta plus I sin minus theta. But you know that cos minus theta is equal to cos theta, but sin minus theta is equal to minus sin theta. So this is minus I sin theta. On the basis of this Euler's formula, you can simplify it. A e to the power I omega t. That will be, on the basis of this result, you can see this can be written as a cos omega naught t plus I a sin omega naught t. And b e to the power minus I omega naught t, this will be equal to b cos omega naught t minus ib sin omega naught t. Okay. So now substitute this expression in your result, which is u equal to a e to the power I omega naught t plus b e to the power minus I omega naught t. You can see when we will actually add these two. Let us take the first two terms added. First of all, here cos omega naught t will be common and the remaining factor will be a plus b. And when you will combine the second term, then I times a minus b into sin omega naught t, this will become. Okay, it is clear. But what is this u? Actually we have considered that x plus iy is equal to u. We have already considered it. See here, I have considered that this x plus iy, this is equal to u. So at the place of u, now again we will write x plus iy, and that will be equal to a plus b times cos omega naught t plus I times a minus b sin omega naught t. Now you know, if two complexes are equal, the real part of the two complexes are equal and the imaginary part are also equal. Okay. So x, which is real part of x plus iy, that will be equal to the real part a plus b times cos omega naught t. So you can see I have written x equal to a plus b cos omega naught t. And so cos omega naught t, this will be x divided by a plus b. And equating the imaginary part, your result will be y equal to a minus b sin omega naught t. And so sin omega naught t will be y upon this. Now when you will square these two results and add, what will be your result? You can see this will be x square over a plus b whole square plus y square over a minus b whole square, and the sum of the cos square omega naught t and sin square omega naught t, that will be 1. So your equation is this. This is x square over a plus b whole square plus y square by a minus b whole square, that is equal to 1. Can you say, in accordance with coordinate geometry, this equation represents which shape? Actually, this is actually the equation of an ellipse. And so you can say that the bob of this Focault pendulum traces out an ellipse, and the origin of that ellipse is at the point 0, 0, 0, 0. Okay. Or you can say at the center of the ellipse. So one part of the problem has been explained or proved. In first part we have to prove that the bob will trace out an ellipse. So this result shows that the bob of this Focault pendulum describes an ellipse with the origin at 0, 0. Okay. Now the next part of the problem is to prove that the earth is rotating. Earth is a rotatory object. we have to prove. Now you can see the complex factor e to the power minus I omega zt is actually superposed here in this equation 4. Although while finding the equation of trajectory, I have neglected it, but this is not 0 but negligible. Sorry, not negligible, but I have taken its value 1. Okay. So it is actually superimposed on this factor, and this factor which is inside the bracket represents the ellipse. So you can say that actually the complex factor e to the power minus I omega zt superimposes a rotation on the ellipse about the vertical z axis. So this ellipse will be not static, but this ellipse will rotate about the vertical axis which is z axis, and this is indicated by this factor e to the power minus I omega zt. And the rotation of this ellipse will take place with an angular velocity omega z, and you know omega z is equal to omega sine lambda. This is actually the vertical component of the angular velocity of the earth. Okay. So if you want to find what will be the period of this rotation about the vertical axis, you know, when we divide 2 pi by the angular velocity, then we get the time period. So the period of rotation about the vertical axis, if it is denoted by tau, that will be 2 pi divided by omega sine lambda. Okay. So this equation 7 actually gives the rotation of the plane of swing of pendulum about the vertical axis as it is indicated in this equation 7. And when you will actually find the value of this period of rotation at the poles, you know, at the poles lambda is equal to 90 degree. So omega z, which is omega sine lambda, that will be omega sine 90, and that will be equal to omega. So when we suspend the pendulum above the poles of the earth, then the time period of the pendulum will be what? That will be 2 pi by omega, which is 24 hours. So you can say that the plane of oscillation of the pendulum makes a complete revolution at the poles in 2 pi by omega time, which is equal to 24 hours. This actually verifies, this is actually the relative velocity. Actually, observer is standing on the earth, and earth is rotating with this velocity, and this in this time 24 hour, earth completes one rotation, and the observer feels that the pendulum makes a complete revolution in this period. So this actually verifies that the earth is a rotating object. Okay. In fact, when you talk about other latitudes, you know, the latitude of a place lambda lies between 0 and 90 degree. It means the smallest value of lambda is 0 at the equator, and largest value is 90 at the poles, and at other places the value of lambda will be greater than 0 and less than 90. And you know, if lambda is less than 90 degree, sine lambda will be less than 1. So in this case, what will be the value of this tau? That will be 2 pi over omega sine lambda, and you have seen that actually this 2 pi by omega, we have already obtained that this is 24 hours, and we will divide it by sine lambda, but sine lambda is smaller than 1. So after dividing by sine lambda, which is a number smaller than 1, you will get a result which will be greater than 24 hours. So I have written here that at other latitudes not situated at the poles and at the equator, this tau will be greater than 24 hours. But when we will talk about the point at the equator, you can see at the equator lambda is equal to 0, and so sine lambda will be 0. And what will be tau? Tau at equator, let us say this is tau e, this will be 2 pi by omega into 0. So this will be simply infinity. So you can say that at the equator the time period of rotation or revolution of the plane of oscillation of the pendulum will be infinite. Okay, so it will actually not oscillate there. When time period is infinite, it means no rotation, no oscillation. Okay. In fact, it is seen that the observer finds that the plane of oscillation of the pendulum is clockwise in northern hemisphere and anti-clockwise in southern hemisphere. Okay, and so you can say that the relative angular shift of the plane of oscillation of the pendulum over a long period not only provides a proof of the rotation of the earth about its own axis, but also enables us to measure the value of omega. So I hope you have understand how by the famous experiment, that is Focault's pendulum experiment, it was confirmed that the earth is a rotating object and the frame attached with it is a non-inertial frame. Apart from that, in this theory, we have also seen whenever a question will be asked in your examination, that so that the bob of the Focault pendulum traces out an ellipse, then you will have to show this result. Okay, this result defined in equation 6. But if it is not asked in your examination, you can escape it and you can directly write this result which I have mentioned in this equation 7. Okay, to prove that earth is a rotating object. Okay, so I think in these two lectures, after these two lectures, your concept about the Focault's pendulum will be now very clear. Okay, so let us wait for my next lecture, something new for you in classical mechanics, and hope you all are doing well. Thank you very much.